All right. So we talked last time a little bit about conversion factors and how they are statements that kind of equal 1, we say. Meaning that if you multiply something by them or divide something by them, you don't actually change the value. You might change the units, but the amount is still the same. And how these conversion factors can help us solve problems, right? So here's an example of a question. If we're given the information that 2.205 pounds for every kilogram, which of these down here is an appropriate conversion factor for that states that information in the form of a conversion factor? Maybe let's look at C and D. What do you think? Do either of those look right?
No.
What's wrong with them?
Well, C and D is basically saying the same thing. That's 1-to-1 ratio.
Okay, very good. And we know that it's not. Excellent. How about A and B? Do either of those look right?
They both have the same numbers, but different units, and so B has the right units with corresponding to the right number.
Okay, that's right. Excellent. And then if we take that information onto this question here, given that 2.205 pounds is 1 kilogram, what's the mass of 23.3 pounds expressed in kilograms? Now, this is a question you could ask Google, and it would spit out a number for you, right? But that's not what we're interested in. What we're interested in is the model, setting up the not necessarily the model, but the blueprint, the dimensional or unit analysis in which we can see the solution in front of our eyes. So what do I got to do? What do I got to do to set this up?
So we begin with the equal sign.
Very good. Equal sign. Then what?
Then we take a deep breath and make a long line to the left.
That's right. And I like to go all the way to the end. You know, I'm a big fan of conserving paper, but I think that it's well worth its use when we're learning these important principles. So, and I don't know exactly how much space I'm going to need to have all the time, so I like to give myself plenty of space. Okay, so what's next?
We put the unit on the right side that we're looking for. In this case, we're looking for the kilogram.
Very good. We're looking for kilograms. Excellent. What's next?
And then on the left side, we start with our first, the line through, and we're going to go with pound, the 2.205 pound.
Well, we could.
Well, wait. Yeah, I guess we could.
But the problem would be if pounds were going to be on top, and we'd have to get to kilograms somehow, right?
Right.
We should probably start with what? Instead of the 2.205?
Yeah, go with the 1 kilogram.
Okay. If we went with the 1 kilogram up here,
okay,
then what would go underneath it?
The 2.205
pounds.
Pounds, yeah.
Okay, very good. Now, in this case, we have pounds on the bottom that we need to get rid of. So to get rid of something on the bottom, you need to have the pounds up
on
here.
Top.
That's right.
Yeah.
And that would be what? What number would it be there?
So that would be 1 pound.
It would
No,
be...
I'm sorry. It would be, so we look at our, the problem and it says 23.3 pounds.
There you go. 23.3 pounds. Excellent. So we can see through this little setup that we have that the pounds drop out And 23.3 divided by 2.205 is the appropriate math to get us to our kilograms. Okay? Very good. Now,
Would it work if we had inverted all of those? It would just be more complicated, but would still work, right?
if we inverted the 2.205 pounds per kilogram?
Yeah, and also if we invert that, we'd have to invert the other. We'd invert both of them.
Well, let's see what would
So
happen.
that we'd still have them cancel out, right? But
If I put in 2.205 pounds for every 1
Yeah.
kilogram,
right,
then the 23.3 pounds would have to be down here, right?
right. Oh, I see.
And then my units that I'm ending up with would actually be 1 over kilograms. So if you did this in the calculator, if you put in 2.205 divided by 2.205 divided by 23.3, all right, I get 0.0946, but that's in units of 1 over kilograms. So if I go 1 divided by that 0.0946, then I'll get the 10.6. All right.
So it does work out. It's just a lot more confusing.
In the end, we won't get kilograms. We'd get 1 over the kilograms. So we have to invert that.
Oh, and then we invert that. Okay.
But another way to do
All
it,
right.
another way to do it would be just to show that we're looking for kilograms, and then start with the 23.3 pounds. And then we can go from pounds to kilograms using our 2.205 pounds for every kilogram.
Right.
And then we would just take our 23.3 divided by our 2.205, and that's our 10.6.
Okay.
Okay, good. So a couple of different ways that we showed to let me see which ones we have here. So yeah, we showed to solve this problem here, right? We got 2 different ways. And in both scenarios, all we really had to do, we had to make sure that our units ended up as kilograms, what we were after. Here we started with the conversion factor first and multiplied by pounds. And here we started with pounds and multiplied or divided by the conversion factor. Okay, good. Great examples. So, here's one more for us. One more.
Okay.
They provided one of the conversion factors for us. 2.54 centimeters is 1 inch. And then they're asking, how many kilometers are there if we have 25 feet? How many kilometers is 25 feet?
Okay.
Okay, so why don't you talk me through this one? Hopefully we don't get that too small so that you can't see it. What goes to the right of my equal sign?
So it's going to be kilometers.
Very good. What do I start with?
And then we're going to start with how many kilometers are there in 25 feet? So we'll start with 25 feet.
Yeah, 25 feet. Very good. What's next?
Okay, I gotta stop you here because I also have impulse when I read that problem to say, oh, I set this up wrong. I want to put feet at the right side of the
Equal sign?
have it just switched, and I guess that could work too, right?
If we wanted to know what?
I had an impulse there to put if we were to set this up again, to do it just the opposite way, have the kilometer over where the feet are, just exchange positions. Could that work too?
I don't think so, because what we want to the right of the equal sign are the units that we're trying to solve the problem
That we're
in.
trying to look for. Okay.
Yeah. And we
So if
already
it's
know
in how
25
many,
feet.
there's your clue, right?
Yeah, that's right. That's one of the clues.
Okay.
Okay, so what's next? What can we get for pretty much 0 brain cells?
So we're going to put feet down at the bottom.
Yeah, there we go. Now, do you know how many kilometers there are in a foot? Or, yeah.
I don't.
I don't either. So let's go to something we know. What do we know about feet?
Okay. Well, we know that there's 12 inches to 1 foot.
All right, so we'll go to inches.
Okay.
And you said 12 inches for every 1 foot. Is that right?
Yeah.
Okay, so then what goes down here now?
Inches.
Inches. Very good. What are we going to try to convert the inches to?
And now we know that there's 2.54 centimeters per 1 inch.
All right, good. So does that mean we get centimeters down here?
Yes.
What are we going to convert the centimeters to?
And then we'll put to meters.
Meters. Very good.
Or if we knew, yeah,
Or if we knew kilometers, we could go right to kilometers. But
right.
just choose the easy one. It doesn't take much
Yeah.
more effort to choose the easy one there.
And is it a hundred? No, it's centa. Is a
Centa.
100? Is centa 100 or 1,000?
Yeah, centa, a cent, century, right?
Okay, so 100 centimeters
For every
and
1
1
meter.
meter. Yeah.
Very good. Now I'm not quite there. I'm still just in meters. What do I got to do?
Right. So now we can go meters. We'll put kilometers on top,
Okay, very good. Kilometers.
and meters. I think there's, well, we know kilometers, so 1,000 meters
Very good.
into 1.
1 kilometer. Excellent. And then with our calculator,
Right.
25 times 12 times 2.54 divided by 100 divided by the 1,000. I'm going to leave out multiplying and dividing by the ones. And the answer there is 0.00762. I'm going to write that down here. That's how many kilometers. How about how many significant digits? How many significant digits should this answer have?
Well, with the, it should have how many significant? Oh, I see.
How many did we start with over here?
Well, we start with just 2, right?
We started with 2, and all of these are just conversion factor or definitions. They're definitions. These
Okay.
aren't measurements, right? 1 meter is 100 centimeters. Nobody is measuring it and trying to find out how many it is. So because all of these are just definitions, it's not going to change our number of significant figures. So I'm still just going to have 2 significant figures. So that's going to be 0.0076
Okay.
kilometers. So
And so you might have lost me, but I get it that well, the 2 zeros don't count as significant numbers, or
That's
3
right.
zeros there, right?
yeah, those
And
zeros in front. don't.
we're going with 2 because of
because of the
25 feet?
That's
or
right.
Is 2 or
the
okay?
25. The 25 is just two significant figures.
And that's what's going to dictate then how many
That's right.
significant numbers we have, right?
Yeah. So do you
Okay.
see 0.00762 or 76 kilometers up there as an answer?
Right.
Do we see it up there?
Oh, do I
0.0076?
see it on the top?
Yeah.
I see it rounded off. Oh no, let's see. No, I don't see it.
No. So we'd have to go with none of these, right?
Right.
That's right. The answer is 7.6 times 10 to the minus 3. Remember how that works? We move the decimal place over 3 times. So it's, 0.0076 kilometers. Okay, good job. Now, I'm going to introduce to you a new concept. Well, it might be new. Might have heard of it before. I'm sure you've heard of the term density, but it's an appropriate time to introduce density for a couple of reasons. One, because it is a combination of units, and it can be used in a way as a conversion factor, like a lot of things can, and we want to kind of have a conversation about how we have multiple ways of kind of expressing conversion factors. So one thing that we can think of, one way of thinking about our conversion factors, is if I draw an apple here, and if I show the apple having 6 seeds, right? Well, we can create a conversion factor then that says there are 6 seeds for every apple. Okay? So it's not like the apple part is equal to the seeds part, but this statement, if I'm trying to identify how many seeds there are or how many apples resulted from the number of seeds, then I can use this kind of conversion factor. And I also, of course, have the other conversion factor that says that every apple, one apple, has 6 seeds. So density becomes a conversion factor simply because what density is density is a ratio of a mass or an object's mass to the volume. Okay? And typically, the units for mass are grams, and the units for volume are milliliters. So, grams per milliliter are typical units for density. All right? So, let's talk a little bit about this really quick. Sometimes we have an object that is perfectly formed, and we can look at the object's the length, the height, the width of the object, right? X, Y, and Z. And we can say X times Y times Z will equal the volume of the object. And so if I put this object on a scale and find out that it weighs 2.35 grams, for example, and if I find the volume equals 1.2 milliliters, then I can take the mass, 2.35 grams, and the volume, and I simply take the 2.35 divided by the 1.2, uh, 2.35 divided by 1.2, 1.96 or 2.0, I guess, if we round it with two significant. I'll put another one in there, 1.96. And then that's our density, 1.96 grams per milliliter. Grams per milliliter. All right. So I have the material here. I found out its volume by multiplying the sides of the cube, and I got its mass, and I put the mass over the volume to give me the density for my material. Okay. Now, sometimes you don't get a nice clean object like that. Sometimes you just get kind of an odd shaped object. And you can find the mass, you can put it on the scale, and you can find out that the mass is 1.073 grams, let's say, whatever it is. But the volume of the material might be more difficult to measure. One trick that we have, though, and this is what I think it was Archimedes, I can't remember, the gentleman who identified that the crown was made of gold, or wasn't made of gold, right? The way that he did it was to, without taking the crown and melting it down and finding out, because it was a beautiful looking crown, he identified what the density of the material was by taking the crown and dipping it into water. So if the volume of this water right here is 1.35 milliliter, no, I should say 11.35 milliliters, and then I put my object into this container of liquid. It doesn't need to be water, it can be whatever, and the liquid rises to maybe 23.07 milliliters. Well, the dispersed volume here of liquid was due to the volume of my mass, right? So how can I find the volume of this mass from this information?
So you would subtract to get the difference.
All right. So I would subtract what number from what number?
So you would subtract the 1.35 from the 2307.
All right. 23.07, subtracting the 1.35 from it, and I get 11.72. 11.72. So that is my what? My mass or my volume?
That's your volume.
And what are my units?
And so so that's volume. And then the
units.
Milliliter, I'm sorry.
Yeah, milliliters. Okay,
Right.
so now how do I find my density?
And so the density we have in grams, 1.073.
That's not the density, that's the mass, right?
Oh, I'm sorry, that's the mass. Yeah,
Yep.
We're looking for density. So we're going to multiply.
We're going to take the mass and divide it by the volume, right? Does that make sense? Because density is the mass of the material.
Yeah, I was getting the things confused. That's right.
That's good. That's fine. So I got 1.073 divided by our volume, and that gives us our density of 0.094 significant figures, 155. And the units are, again, grams per milliliter. 0.09155 grams, and you can think of it as for every 1 milliliter of that material. Now the density of different materials is different, but if it's the same material, if I have a little pile of some gold here, and I have a bigger pile of some gold, both piles have different masses and both piles have different volumes, but they have the same density. Same density, right? Because the
Okay.
density is the ratio of the mass per volume. Ratio of the mass per volume. So, let's see if we can answer some of these questions now. Here's a glass bead with a mass of 5.96 grams, and I drop it into a beaker of water that contains 10.2 milliliters. If the resulting volume is then 12.3 milliliters, what is the density of the bead? What do I got to do to solve this problem?
So we have to first subtract. We're going to find the volume, and so we'll have to have 12.3 milliliters minus 10.2 milliliters to
Okay. Good. So that's 2.1 milliliters.
volume. Okay. And then we have that divided by, let's see, it's mass divided by volume, right?
That's right.
So it would be the 5.96 over the 2.1, and that would give us our density.
Okay. So we got 2.03,
Okay.
and we have, 2.83. That's an 8, not a 0. 2.83, and we only have two significant digits, right? Because our bottom one has two significant digits, and this is a division problem. So we're going to stop it at 2.8 grams for every 1 milliliter. Okay, very good. Excellent job.
So can you go back to that equation again on the paper?
Mm-hmm.
And okay. Yeah, I got it.
All right, excellent. Okay, so here's another one. A sample of metal X has the same mass as a sample of metal Y, but the sample of metal X has a smaller volume. So we want to know which metal, X or Y, has a greater density. Which has a greater density. Okay, now to kind of solve this problem here, I'm going to draw some pictures for us. I'm going to draw pictures of those two piles of X and Y. So here, how should I draw them in terms of their volume? Which one has a larger volume, X or Y?
So Y's got the bigger volume.
Okay.
Or I'm sorry, X has and X has the smaller volume. Okay.
That's right. Very good. So there they are. Now, what do we know about their masses?
So the masses are the same.
Okay. Their masses are the same, but X has a smaller volume. Is that enough for you to determine which one has a greater density or no?
Yeah.
Really? What do you think?
I think that Y would have the greater density.
Okay. So let's give some volumes here. Let's say that this volume is maybe 4. Is that okay? Just for fun?
Okay.
And let's say this one is volume, and they'll put on their milliliters. And this one is a volume of about 1 milliliter. All right. Now let's throw in some masses for us. Which one has more mass?
Y.
Okay. Let's call that 10 grams. And can we say that this one has only 4 grams? Is that okay?
Well, why would have the greater mass?
But it doesn't say that. Oh, no, they're supposed to have the same mass, aren't they?
Oh, they do. Yeah. Okay.
Okay, so 10 grams.
Where did they go? One. Okay. Yeah.
All right, so if they have the same mass, but different volumes, can we calculate what the densities are here?
Yeah. I got that answer. Yeah, we can.
What is the density for X?
Okay, so density equals the mass over the volume.
Uh-huh.
So for X, it would be 10 grams.
Very good. The density of X is 10 grams per milliliter. And what's the
Okay,
density
and then
for Y?
for Y, we would have 10 over the 4.
2.5.
Yeah.
That's the
So X
density
has
of Y. So X has the greater volume, or density, greater density, sorry.
yeah.
Okay, very good.
So at face value, I had said that Y, but at face value, before we did all this, I could have just looked at the ratios and realized that that X had a bigger density, that it's not based on the size of the.
Right. It's not based on
What
its
am I
volume.
trying to say?
It's not based on its volume. It's the ratio between its mass and its volume, right?
Right.
Okay. Very good. We have a couple more for you to try. Here's
Okay.
one. It looks like it's exactly the same, but this next one is a different question. Can you tell the difference between this question? What is this question asking?
Okay. Let's see. X has the same volume as Y. But the same, let's see, but the sample in middle Y has less mass. Okay, so now the difference is it just changed from the last one, just changed the units, right? So the volume's the same, but the mass is going to be different.
Okay, so we got the same volume.
And
Let's say that they're both 10 milliliters.
okay.
Which one has a greater mass?
And then X.
X has a greater mass. That's right. So let's say 10 grams here and maybe 5 grams there. Is that okay?
Okay.
So which one's going to have a greater density?
It's interesting.
Remember, density is...
The X,
That's
X
right.
will have a greater density.
That's right. X has a greater density. Very good. So this one here, I'm not going to let you do it, but I'll talk about it here.
Okay.
A sample of metal X is simply because it's just a little too much maybe at this point. But a sample of metal X has the smaller volume. So we'll draw it here. Okay. The sample of metal X has a smaller volume than Y. And the sample of metal Y has a greater mass than metal X. So if Y has a greater volume and a greater mass, because we don't know how much of a greater mass it has, we can't tell. We're not going to be able to determine the difference in density there. Okay? What? Yeah. So, we'll skip to this. We have a couple more slides here, and we're almost done. But we want to use the density of a material in such a way that it's used as the conversion factor now. So here's an example of how the density of blood, 1.05 grams for every 1.00 centimeter cubed or milliliter. Or we could write it the other way again, 1.00 centimeter cubed of blood for every 1.05 gram of blood. Those are different conversion factors that you can get from the density. So let's see if we can use the density as a conversion factor to answer this question. So there's a crash in the lab. A large vial of mercury falls onto the ground, and we call hazmat, and they want to know what mass of mercury is on the ground. We know that the bottle says 2 quarts, and the bottle spilled, so 2 quarts fell on the ground, but they're asking how much mass of mercury is on the ground. Okay? So we need to set up a dimensional analysis to answer this question. All right? We start with an equal sign, right?
Okay.
What goes to the right of the equal sign?
It's going. Oh, to the left?
To the right.
My left.
What
To the right.
What
Yeah.
goes to the right of the equal sign?
Right. We're looking for the volume. I mean, where are we looking for volume, right?
What does it say? They ask for the mass.
Oh, they're asking for the mass.
Yeah.
Okay, so that's going to be in grams or
Okay.
Hg.
Grams of Hg, grams of mercury. Very good.
Okay.
What goes to my top left?
Okay, that's going to be the liter.
What do they give us? What do we get? What do we start with?
And
The 2 quarts.
yeah.
All right. Now you could start with this.
Oh yeah, that's right.
Liters per
We're
quart.
going to go with quarts.
Yeah, I think it's going to be easier for us to think about if we start with
Quarts on top.
the 2 quarts of mercury.
Okay.
What goes down here now?
Quarts.
That's right, quarts of mercury. And now we're going to convert that quarts to what conversion factor can we use?
And then a liter to quarts.
Yeah, to liters.
Right.
Liters. So, I mean, yeah, we can write in there mercury. It doesn't matter what it is. The quarts to liters ratio, regardless of whether it's mercury, water, gold, whatever, same ratio. But it says there, I guess, 1 liter,
1 liter
1.0567, right?
Right.
Okay, very good. Now I have to get rid of the liters of mercury. What am I going to want to do with that? What am I going to want to convert liters of mercury into?
Into the okay, I need to look at this.
They've given us the density here, which tells us the
Oh,
grams
the density.
per
Okay.
milliliter.
Grams over milliliter, right?
Yeah.
So then we want to go from liters. We want to have milliliters.
Very good. Milliliters. Do you remember how many milliliters there are in a liter?
1,000.
Very good. 1,000 milliliters for every liter. Great. Now we're in milliliters, and now we can go to what with our milliliters?
And then we go from well, up to
We can use the density here, right? Because it tells us
that's right.
how many grams there are for every 1
That's
milliliter.
right. Yeah.
So we can go right to grams of mercury, right? And that's where we wanted to be. So we're going to now use the density. So how many grams of mercury for every milliliter of mercury? Can you see that?
Yeah. So it's 13.69 grams for 1 milliliter.
Very good. So I can see the milliliters of mercury cancel out, liters of mercury cancel out there, and quarts of mercury cancel out there. So I just need to take the 2 divided by 1.0567 times 1,000 times 13.69. And that will give me my grams of mercury, which here ends up being 2.6 times 10 to the 4th. So if we do this in the calculator real quick, we'll see 2 times the 1,000 times the 13.69 divided by the 1.0567. All right. And then that should be our, it says 25,910, or keeping to our 2 significant digits, 26,000 grams. Okay. Very good. Did you follow that okay?
Yeah, for the most part, it's you know,